Hello and welcome. My name is Alexis BENAITIER. I'm a member of the Christendopler Laboratory for Innovative Control and Monitoring of Automotive Powertrain System, and I will have the chance today to introduce you one of our research topic that is a predictive control strategy of nonlinear multivariate systems applied to hybrid powertrains. So first, let me introduce you some background and context. Nowadays, most of the trucks are turning hybrids. So that means that they will have two different power sources, and in our research we focus on hybrid powertrain with on one side a diesel engine, on the other side an electrical unit, and how to split the power between these two elements. This hybridization comes toward the ultra-low emission vehicle, which have mostly two objectives. The first one is to minimize the fuel consumption, and the second one is to stay below some emissions thresholds that are defined by the European Union, for example. Our control strategy should minimize this or fulfill these objectives, but should also include and take advantage of all the predictive information that we can collect from the GPS or from the onboard sensors, for example. Also, we have to meet some constraints for the system, and our strategy has to be applicable for different configuration of the hybrid powertrain system that we want to consider. In our general concepts, we have three main points, which are the strategic level, tactical level, and sensor fusion. Strategic level is to define the route-wide or the long-term strategy, for example, how to split the engine and the engine torque and the motor torque. The tactical level will be how to control each element, for example the engine or the electrical unit on its own, to match the strategic level strategy that we defined beforehand. And the last point is sensor fusion, which consists in taking advantage of all the sensors that are available to build some really accurate and robust estimates that therefore can be used by the strategic and the tactical level. Now, before going into the details and results I want to show you today, let me just remind you that this project is part of a program that is a 7-year cooperation directed by Dr. Christoph Ametner between Avialist and the TU Wien. Among all the research directions, so there are 3 research directions, the one I will be talking about today is predictive multi-level control and operating strategy. So as we've seen before, there's these 3 topics, and now I'm going to detail all these 3 topics. So the first one is the strategic level. So for the strategic level, we will consider a hybrid powertrain, once again, of a truck with a diesel engine, an electric motor, a gearbox, and an exhaust after treatment system. And to control this system in a so-called cooperative strategy, the first thing we need to do is to split all these components into agents. So we have one agent for splitting the torque between the combustion engine and the electric motor, one agent responsible for the gearbox, and the last one for the after-treatment system. Of course, there are some interaction between all these elements, and so each agent should consider all the objectives of the hybrid truck and not only the local objective, and this is why it's called the cooperative strategy. Also, we need to make sure that it's feasible so that we can fulfill all the shared constraints, and we have to make sure it's optimal. That means that once again each agent has to consider all the objectives. The strategy we developed is basically composed of 3 elements. In the middle is the control element. The control is really simple. Each agent is based on a simple parametric model, so it's just a deterministic model that depends on some parameters called capital P here. Then in the arbitration layer, it's not really important. It's only here for the implementation of the strategy, because for example we can have degraded mode if one sensor is not doing its job accordingly. The optimization layer is the most important because it's where all the parameters are being optimized. So we can optimize the parameter online, offline. We can also do it all at once or agent after agent, so synchronously or asynchronously. The key point here is that when we're optimizing the parameter for one agent, we already know all the other agents' simple parametric model, so we can optimize it with all the objectives of the full plant dynamics. Now let me show you some results. So these results were shown for the torque split and gearbox, so without exhaust after treatment system, where we have different objectives to follow the battery state of charge, which is here the reference at 50%, also limit the number of gear shifts and minimize the fuel consumption. First, let me introduce you the PMP results, so Pontryaghin's maximum principal result, which is an offline result and only trying to optimize the fuel consumption. If we look now at the cooperative result, first for the gear shift, you can see that there's way less gear shift, and that is really good because it means that this solution is feasible. Then in terms of SOC, it's perfectly following the 0.5 or 50% charge of the battery, and in terms of fuel consumption, it's really close to the PMP. So this is a really good result in terms of nonlinear control of multivariate system. The advantages of this method is that we can add or remove agents, we can have different agents type, and its real-time capability because all the optimization can be done offline. Now let me switch to the second topic, which is the tactical level. Now that we've defined some reference to follow for the strategic level, for example the engine power or engine torque, we need to look at how we can fulfill this torque at each time. So here if we focus on the engine, one sub-part of this component is the engine airflow, and so our air pass. So you got fresh air entering the compressor when it's compressed, going to the intercooler, then to the throttle and then to the engine. And after the combustion, the exhaust gas goes to the electric turbo. So electric turbo is one of the actuator, it's the speed of the turbocharger, and goes to the exhaust after treatment system. Also the EGR is the second actuator, it allows some flows from the exhaust to go back into the intake and so to control the NOx. Here the two set points are the exhaust pressure and the NOx, and they come from the strategic level. We've developed a nonlinear controller for a multivariate system such as this one, and you can find all the details in the publication. In terms of results, we've tested this controller onto a real system, so onto a test bed, where the engine speed and load are constantly changing, so it's close to real operation. We have some constraints on the turbocharger speed and on the EGR, and we want to follow some reference in the exhaust pressure and NOx concentration. As you can see, the test bed results are really good because they are really close to the reference that we want to track, and the turbocharger speed and the EGR opening in percentage, which are our two inputs, are perfectly inside the constraints. So here we just demonstrated that this controller works really good. It's a simple system identification, calibration is intuitive, and it's a nonlinear controller because we have different models for different operating points, but at each time step we only have to solve one model predictive control that is a linear model. Also, we do not need any observer because each model states is based on the output and their derivatives. Now that we've seen one application of the tactical level, that brings us to the last question and the last point, which is how we can have accurate and robust estimates for the controller. And this will be covered by this sensor fusion topic. So if I keep using this example of the diesel air pass, most of the controller nowadays need some estimate of the fresh air mass flow entering the cylinder and at the lambda exhaust. Lambda exhaust is nothing else than the oxygen content in the exhaust gas. So we have a bunch of different sensors on our model, and the problem is that these sensors are inaccurate during transient, and sometimes we're just no possibility to have a sensor, for example, for the fresh air mass flow. And so in that situation, sensor fusion will be the gathering of all the sensors and also to build a dynamic model to try to compensate for the inaccuracies during transient or the signal that we cannot measure, basically. So from a theoretical point of view, for a regular observer or a simple observer, we take all the available sensors that are available, we build a dynamic model, and we directly get some model output estimate. The problem is that the states are never corrected, so the model can diverge or can just have an offset. In the sensor fusion, With the sensor fusion, now we're considering the model output estimate, but also sensor output measurement. And so when we're comparing the model output estimate and sensor output measurement, we can correct the dynamic model. And so just as an example, the sensors in our case are really accurate during stationary operation, whereas the dynamic model is accurate during transient operation. So based off how much transient we are in currently, we can just arbitrate between those two and correct the states, and in the end have a robust and accurate estimate. So we have tested that on simulation, where we want here to estimate the fresh air mass flow. As you can see, a simple static model is not doing a good estimate because there's some offset and the transient are not perfectly captured. Whereas for the Kalman filter, it's really accurate and it's really close to the reference. For the air to burn gas ratio, also called lambda exhaust, it's even harder to have a right estimate because of some stronger nonlinearities. So here the static model has some large offset, time shift, and also some overshoot, whereas the measurement has less overshoot, but is also have a really big time shift and a lot of noise. And for the Kalman filter, once again, it's much closer to the reference, and this signal can actually be used by the controller and give really good results in terms of NOx and soot emission, for example. So now I've introduced the three topics that works together to build, more generally speaking, some nonlinear multivariate control of any system. So here it was demonstrated for a hybrid truck, but it can be used for other systems. Of course, it's working with nonlinear system. It's a cooperative method for the strategic level that is also linked with the tactical level, where we developed a multivariate predictive control method, and the sensor fusion that is here just to provide all the different estimates that we need for the strategic level and the tactical level. So I would like to thank you for the interest that you're showing in our research topic. Also, feel free to contact any one of us or to visit our website if you want further information. Thank you.